Welcome back to AP Chemistry, section 1.5, and at 1.5 it goes over the atomic structure and electron configuration of atoms. And so before we talk about the details of what an electron configuration is, let's just talk about how we're going to write an electron configuration. And so to write an electron configuration, we can use a periodic table. And so we'll pull up a periodic table right here. And what you want to do is you want to label the S, D, and P blocks, which are going to be located right in here. And this right here, everything in the atoms right here are going to be in the S. Everything that's going to be between these two is going to be the D. And then over here, we have the P. Now, you want to watch out because right here, this helium, this is also part of the S block. And there's also going to be an F block, and the F block is at the very bottom. I cut it off the periodic table, but it's going to be two rows right in here, and this would be the F block. And so we're not going to talk about the F block in this video, but know that the F block is going to be down here. And so what you want to do is, after you label the S, D, and P block, is you want to put some numbers down. And those numbers are going to look like this, where you're going to have a 1 right here, and you'll go all the way down until you get to 7. And over here on this P block, you're going to start off at the 2P and not at 1P. And when you get down to the F block, you're going to have 4 and then 5 for the 2 rows for the F block. And where you want to watch out is this right here. The D block in here, it starts off at 3, not at 4. So after you get your numbers down, you're going to start at the top left right here, and you're going to go from left to right and from top to bottom. And what you're going to do is, when you start this top left right here, you're going to be in the 1s category. And so to write the electron configuration for this, you're going to put 1s1. And this 1 right in here, that represents the number of electrons. And for right now, we're just going to worry about doing these electron configurations for neutral atoms. And so the number of electrons that are going to be right here is going to match the number of protons. And so we can count the number of electrons by counting up these numbers right in here. And so if we want to stop right here, this would be the electron configuration for hydrogen. And if we want to get the electron configuration for helium over here, we would just go from left to right, and that would be the electron configuration for helium. We would say it's 1s2. Now, what we'll do now is we'll just keep on going through all these. And so if we go to the next one, we're going to be in the 2s block. So we're going to have the 1s2, and then we have 2s1 right in here. And so if we stop here, this would be Li, or lithium. And so you can see how we would keep on going on to figure out the electron configurations for each of these atoms. And you may notice that as I move through each of these electron configurations, when I get to the end of this P block right in here, the maximum number of electrons that this P block can hold is going to be 6. And after I reach the 6 right here, I have to move on to this S block over here. And this S block can hold a maximum of 2 electrons. And that's why there's going to be a 2 right in here. And so I can move on to each of these electron configurations. And you may notice that as I move through all these electron configurations, when I get to this D block right in here, the maximum number of electrons that this D block can hold is going to be 10. And when I make it all the way to the end of this D block right in here, you can see that the 10 is going to be right in here. And after I reach this 10, I have to move on to this P block right in here. And so if I stop right here, this would be the electron configuration for arsenic, or As, on the periodic table. And so if we keep on going to all the way to the end here, we would get to Kr, which is krypton. And if you look at krypton, you'll notice it has 36 protons. And if it has 36 protons and it's neutral, it's going to have 36 electrons. And so this right here is going to be the electron configuration for krypton whenever it's neutral. So let's say that you want to find the electron configuration for something like silver, which is Ag. And so silver is going to be right here on the periodic table. And to get the electron configuration for silver right here, what you're going to do is you're going to start right here at the top left, and you're going to move from left to right and from top to bottom. And you're going to go through all these different atoms on the periodic table until you get to Ag right here. And whenever you go through all these different atoms and get to Ag, the electron configuration is going to look like this. So here's the electron configuration for Ag, and instead of writing all this out for Ag, what you can do instead is you can do a shortcut, and the shortcut is to go up right here, one element on the periodic table, and then go all the way to the right until you get to Kr right here. And so what you're going to do is you're going to say all of this right here is the electron configuration for Kr, so we could actually start the process of finding the electron configuration for Ag if we can say this right here is going to be Kr, and we can pick up with the 5s2 right here, and then we'll go all the way here until we get to 4d9. And so what we'll do is just say this right here is going to be the electron configuration for Ag, and this is the shortcut rule. And you can do this for any element that's going to be right here on the periodic table. These are called the noble gases. So you can only say this for Kr right here because it's going to be a noble gas. And so you can do this for Kr, Ar, or Ne, or Xe. Now, there are some exceptions to writing electron configurations, so let's take a look at those exceptions. So if you look at these different elements, this is the electron configuration that we would expect to find. But if you look at Cr and Cu, this 3d4 right here and this 3d9 right here, you need to know that this D block, it likes to either be half full or all the way full. So if you look at this 3d4 right here, it'll actually take an electron from the 4s2 and give it over here to the 3d4, so that the 3d4 can become 3d5, and that way this one would like to be half full. So this one right here for the Cr is half full, and the same thing kind of applies to the Cu. We would have 4s2 3d9, but this 3d9 wants to be all the way full, so it will take an electron from the 4s2 right here and give it to this 3d9 to make it 3d10. So this one would like to be all the way full. And even though we would expect to get these two electron configurations for the Cr and the Cu, what we end up getting is we end up getting this. For Cr, we get Ar, and then we get 4s1 3d5, and then for Cu, we end up getting Ar 4s1 3d10. And so we don't get these electron configurations for Cr and Cu. And this rule applies to all the D blocks, so the same rule would apply to atoms like Ag and Au. So now let's take a look at what this electron configuration means by taking a look at the electron configuration for something like oxygen. Now let's pull up the electron configuration for oxygen, and that's going to look like this. And this electron configuration for oxygen has 4 different quantum numbers. And to get a better idea of those quantum numbers, let's pull up a table so we can see what those look like. And in this table, you can see that the first quantum number that we have is going to be this N value, and that's called the principal quantum number. And what that does is it's going to tell us the distance away from the nucleus, and it's also called the shell. And there are different possible values that the quantum number can take on, and those are going to be 1, 2, 3, all the way up to infinity. Now, it does not include a decimal, and it does not include 0. And in this electron configuration, this number right here, and right here represent that N value. And so this can be N equal to 1, and it can also be N equal to 2 in this case. And it can be more than 2, but for the electron configuration for oxygen, it only goes up to N equal to 2. And so oxygen has 8 different protons in the center. And so what we can do is we can draw out what this electron configuration means over here. And so oxygen is going to have 8 protons in the center, and we just said that this N equals 1 represents the distance away from the center. And so what I'll do is I'll put this arrow right here, and I'm going to say this distance here is going to equal to N equal to 1. And we have these other electrons over here where they have an N equal to 2, and because this 2 is going to be larger than this 1, it means that these electrons in here are going to be farther out from the center. And so I'm going to draw a larger line over here, and I'm going to say this is going to be N equal to 2. And the next quantum number is called the angular momentum, and each of these N values has its own angular momentum. And what the angular momentum talks about is it describes the shape of the orbital, also called the subshell. And this n value right here has an L value, and that's going to be from 0 to n minus 1. And so because this is n equals 1 for right here, this L value can be 0, and it cannot be 1 because n is 1. And this n value is 2, and it's going to have its own L value, and that's going to be L is going to be equal to a 0, and it's also going to be equal to a 1. And what we'll do now is we'll put these different shapes into this orbital over here. Now, when you have an L equal to 0, that's going to represent the S, and when you have an L equal to 1, that's going to represent a P. If L was equal to 2, that would represent the D, and if L is going to be equal to a 3, that would represent the F. And for the AP chemistry exam, you don't need to know the shape of the D or F orbital. You just need to know the shape of the S and the P. And so what we'll do now is we'll talk about how the 1s is going to be a sphere. And so we'll draw in a sphere for that. And this is going to be n equals 1. And a sphere is going to go basically just around kind of like this. And this is going to be the 1s orbital. And now we'll do this 2s orbital. So we're going to start right here for n equals 2, and we'll go all the way around like this. And this is going to be the 2s. And this is going to be a sphere. And then we have the P right here, and this P is going to be this like dumbbell shape. And so what we'll do is we'll make this just one dumbbell kind of like this, and then we'll do another dumbbell kind of going down like this. And this is going to be the P orbital. So this S right here is going to be the sphere, and the P over here is going to be this dumbbell shape. And so what we'll do now is we'll move on to the next quantum number, which is going to be called the magnetic quantum number, or the M sub L. And what that does is it tells you how many orientations there are. And for that, each L value will have its own M sub L value. Just like each N value had its own L value, each of these values will have its own M sub L. And what that's going to represent is going to be the M sub L, and that value is going to be a negative L to a positive L. And so because L is going to be a 0 right here, that means the M sub L when L is 0 is just going to be 0 right here. And for this L is going to be a 0 here, so this will have an M sub L also equal to 0. Now for this L value, the L equals 1, that's going to be M sub L is going to be equal to a negative 1, a 0, and a positive 1. So this right here, this L equals 1, it's going to be M sub L has 1, 2, 3 different numbers, and each of these numbers represents one orientation. So what we'll do here is we need to make 3 different orientations for this P orbital right in here. And so this right here, this is going to equal this up and down. That's going to be one orbital, and because it goes up and down like this, we can call this the Y orbital. And we need another one, so we can have an X orbital right here. So I'm going to do another P like this, and this can represent the X value. And then we need a third, so we can have one of these orbitals is going towards us. So I'll make this kind of darker like this, and then it's going to have to go away from us too. And so this is going to be the Z orbital. And so this would have an X, a Y, and then a Z orientation. And the reason why this L equals 0 is an S has only one orientation is because it's a sphere. And a sphere, you can only hold it one way, and it's still going to be a sphere. Whereas this P right here, we can hold it lots of different ways. But whenever you're doing these orbitals, you can only hold it 3 different ways because we have 3 different numbers right in here. And so what we'll do here is just move on to this next quantum number, which is going to be the spin quantum number, or the M sub S. And what that does is it tells us if the electron is going to spin clockwise or counterclockwise. And so what we'll do is we'll start filling in these electrons in here. That's part of this electron configuration. And so first we're going to fill in the 1s 2 electrons. And so we can put an electron right in here for this 1s here, and we'll call that a spin up. And so we'll have a spin up, which is going to be a clockwise orientation, and then we can have another electron in this orbital, and it can be a spin down, which is a counterclockwise spin. And now we'll move on to the 2s, and so this 2s has one orientation right here, so that would be this one right in here, and that's going to have 2 electrons that we can put in there. So one of these will be a spin up, so we'll put a spin up for that one, and then we want to put another one in here for the spin down. And so now we'll move on to this 2p4 right here. Now the 2p4, we have 1, 2, 3 orientations, and so we're going to start filling those in. I'll start off filling up this this X right here, so we'll put an electron right in here, and this will be a spin up. Now this one right here is a spin up. We cannot put another electron in this same orbital because electrons want to be spaced out as much as possible. So we're going to go on to this next orbital, this Y orbital, and which is also still a p. So instead of putting an electron in this one right in here, which is the same orbital, I'm going to put an electron like right in here, and this can be my spin up. So we have that spin up electron, the clockwise, and so we have 4 electrons right in here. We just used up these 2 right here, and so we're going to put in another one, and this is going to be the Z orientation. So I can put an electron right in here, and we can call this the spin up. And now that we have 3 electrons in here, we need 1 more to get our 4th, and so now we have to double up one of these orbitals. And so we'll double up this one, would be a spin down, and so I'll go into this X orientation, and I'm going to put it right in here, and this would be the spin down counterclockwise spin. And the way that we filled up these orbitals with the electrons is called Hund's rule. And Hund's rule basically says that that each electron, when it goes to fill in, will fill in the lowest energy possible, and to space out the electrons as much as it can before doubling up. And so here are our electrons for this oxygen atom. And one thing you should notice about this is that no 2 of these electrons has all the same 4 quantum numbers. Each of them has a different set of quantum numbers. Like if we were to pinpoint out maybe like this electron right in here, this electron is going to be the n equals 1. So this is going to be right in here, it's going to be n equal to 1, and it's going to be an S orientation. So the L would be a 0 because it's an S, and it's going to have an M sub L value that's going to be equal to 0, and it's going to be a spin up. So it has an M sub S equal to plus 1/2. And the spin up are going to be plus 1/2, and the spin down are all going to be minus 1/2. And so you can see that if we were to pinpoint any one of these electrons, it would have a different set of these 4 different quantum numbers. And this is called Pauli Exclusion Principle. It's called the Pauli Exclusion Principle. So let's say that we want to find the maximum number of electrons that we can put in a certain orbital given a certain principal quantum number. And to find that, we're going to use this equation that the maximum number of electrons is going to be equal to 2n squared. So this n right here is going to represent the principal quantum number. So let's find the maximum number of electrons that can fit in an n equals 1 principal quantum number. And so what we'll do here is just do 2, and then the principal quantum number is going to be a 1. So we'll do 1, and then we square it. And when we do this calculation, we're going to get 2. And so those are going to be 2 electrons that can fit in an n equals 1. And those electrons are going to be right here. Here's the first one, and then here's the second one. And now let's figure out the maximum number of electrons that can fit in an n equals 2. And so that's going to be equal to 2 times 2 squared. And when we do this calculation, we're going to get 8. And this 8 electrons right here are going to represent 2 in this orbital, and then we got 6 in these orbitals over here. And this equation right here doesn't mean that we're going to have to necessarily find 8 electrons. It just means that these are the maximum number of electrons that can fit. And so you can see here that we got 1, 2, 3, 4 electrons in this 2p, but we can actually put 2 more electrons, and that would be 6 electrons in here, and then we would have 2 electrons over here, and that would represent the 8 electrons that this equation represents. And if we wanted to find the maximum number of orbitals that we can have in a certain principal quantum number, well, that's just going to be this equation. That's going to be the equation that the maximum number of orbitals is going to be equal to n squared. And an orbital, you could think of that as just how many m sub l's there are. And so let's find how many orbitals can be in n equals 1. And so what we'll do here is just sub in 1 for this n, and that's going to be 1 squared, which is going to be equal to 1. So when n equals 1, we can have only one orbital, and that orbital is going to be right in here. It's going to be this orbital right here. And now let's figure out the maximum number of orbitals that can be in an n equals 2. And so what we'll do is we'll say we have 2 for the n value, and then we square that, and that's going to be 4. And so there are 4 orbitals that can exist in an n equals 2. And those 4 orbitals are right here. We have one orbital right here for this s. It's going to be this orbital right here. We put the L equals 0. And then we have 3 more orbitals right in here. Here's one orbital, and then here would be another orbital, and then here would be another orbital. So you can see here that we got 1, 2, 3, and then 4. And the 4 right here represents these 4 different orbitals that can exist in this n equals 2. So now let's try to do example question 1 using some of this information. So in example question 1, it says, what is the maximum number of orbitals and electrons when n equals 3? So one way that you can think about doing these types of questions is to write out the electron configuration. And so I'll go ahead and write out an electron configuration starting with 1s2, and then we have 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. And I'm going to stop right here because I reached the maximum number of 3's right in here, where the n value is going to be a 3. And so what I want to do is figure out how many orbitals I have within each one of these n equals 3's. And the orbitals, that's going to be the m sub l value. So I'm looking for how many m sub l's I can have within each of these 3 right in here. And so what we'll do is, for this s right here, that's going to be an L equal to 0. So when L equals 0, the M sub L is going to be equal to, well, we could say negative 0, 0 plus 0, because M sub L goes from negative L to positive L. But that's all just going to be 0, which is just this one number. And so because we have one number right here, that means that's one orbital. And so now we'll move on to this P right in here. And so that's going to be L equal to 1. And when L is equal to 1, the M sub L is going to be negative L to positive L. So that's going to be negative 1, 0, and then plus 1. And now move on to this this D over here. And so that's going to be an L equal to 2. And so the M sub L for that is going to be negative 2, negative 1, and then we have 0, then we have plus 1, and then we have plus 2. So that's going to be 1, 2, 3, 4, 5 different orbitals that have different orientations for the for this D right in here. And so what we want to do is we want to count the number of orbitals. So we're going to have, let's see, we have 1 right here, then we have 1, 2, 3 in here, and then we have 1, 2, 3, 4, 5 over here. And so that's 5 different orbitals. What we could do is just say 5 plus 3 plus 1. That's going to be 9. So we have 9 orbitals when n is equal to 3. And that's the maximum number of orbitals, right? This, just because there are 9 orbitals in here doesn't mean that every single atom has to have all these 9 orbitals. This is just the most that it can possibly have. And now we want to do is we want to figure out how many electrons we're going to have. Well, each orbital can hold 2 electrons, right? So I can have an up arrow here and a down arrow. These are going to be 2 electrons that can fit in this M sub L. I can have 2 electrons in here that would fit in this orbital, and then I could have 2 more in here, and then I can have 2 more in here. And so this would be 2, 4, 6, and then we would have 8 in here, and then we got to finish out these right in here. So we have 1, 2, and this one. We could have 1, 2 in this one. We could have 2 in this one, 2 in this one, and then 2 in this one. So really what we could do is we could just take this 9 and multiply it by 2 to get the number of electrons that would fit. So that would be 18 electrons. And another way that you can answer this question is by doing this equation over here, which is going to be that the maximum number of orbitals is going to be equal to n squared. And so we could just say we have n equals 3 right here. We could just say that's going to be 3 squared, which is going to be 9. And so we could not have to do all of this. We could just use this equation right here and get 9 right there. And to get the number of electrons, because each orbital holds 2 electrons, we could just say that the maximum number of electrons is going to be equal to 2n squared. And so we'll do 2 and then times this n right here, which is going to be this 3, and then we square that, which is going to be 18. And so we could do it this way right in here, where we have the electron configuration given to us, and we can count them like this, or we could just do this equation right in here to figure that out. So now let's move on to example question 2. So in example question 2, it says, what is the N and L values for the following? And it's got A, B, and C. And so the N value, that's going to represent how far you are away from the center, which has all the protons and neutrons. And that's going to be this number right in here. This is going to be that 2. So for this right in here, N is going to be equal to a 2. And then we have this P right here. And when we have a P, that's going to be the shape, which is the L value, and L would be a 1. And now for B right in here, we have this 4 right in here. So that's going to be N equal to 4. And then when you have this D right in here, that's going to be L equal to 2. And when you have this 2s right in here, well, this 2 right here, that tells you the N value, how far you are away from the center. And so that's going to be N equal to 2. And then when you have an S, that's going to be L equal to 0. And so these are all the N and L values for each one of these. And so now let's go ahead and talk about the difference between the ground state and excited state for electron configurations. So to understand ground state versus excited state, we first need to understand how electrons fill orbitals. So let's take a look at oxygen. And right here we have the electron configuration for oxygen. And each of these N values and the S's right in here, for the electrons, they're going to occupy a certain energy level. And we can graph those energy levels on a graph that looks like this. And if you can imagine that right in here, we have the nucleus, and that's going to be where the protons are. Right in here, we have the 1s, and then we have the 2s, 3s, and so on like that. And so as we go up in this N value, the energy level will increase. And as we go from an S to a P, like in here, the energy level will go up a little bit. And if we go from like a 3s to a 3p to a 3d, you can see how the energy level will change going up as we go from an S, P to a D, and it will continue to do that. And so if we have this right here for oxygen, the electron configuration for oxygen, what we can do is we can take these 2 electrons and we're going to put them in the 1s on here. And so what we can do is we can put an up arrow for one electron, and then we'll put a down arrow for the other electron. And now if we go to the 2s right in here, you can see that we'll go from an electron in here, so an up arrow, and then a down arrow. And these up arrows are the plus a half, and the down arrows are the minus 1/2 of the m sub s quantum number. And so when we go to this, the 2p right in here, we have 4 electrons that we want to fill. And so what we'll do is we're going to fill it like this. We're going to put an up arrow, and then we'll go to this next orbital, and so we'll have an up arrow here, and then we'll go to the next orbital, and we'll have arrow in here. And that's going to be 3 electrons, and we need 4. And so the way we do this is we're going to have to double up one of these. So we'll double up this one. And the way that this fills up electrons is called Hund's rule. And Hund's rule says that each orbital in a subshell is occupied by a single electron before doubling up. And that's exactly what we did here. And so a violation of Hund's rule would be something like this. If we did up arrow and then down arrow and then up arrow and then down arrow, all in these just these 2 orbitals. And so let's go and fix that. Let's make it so that we have 1 electron in this orientation, and then we'll put another electron in this orientation, and then electron in this orientation. And now we'll double up because we have to. And so we'll just double up this one right in here. And so this is how the electrons will fill orbitals. And another topic on the AP chemistry exam is something called the Aufbau principle. And what that is it says that the electrons fill lower energy atomic orbitals before filling higher ones. And so this right in here is going to be the lower orbitals, and these right in here are going to be the higher orbitals. And basically what we did was we filled up this this 1s first, and then we filled up this 2s, and then we filled up the 3p. We didn't fill up this one first and then move to this one and then do this one. The way we filled it up was we went here first, here second, then here third. And so if we were to add another electron in here, we could put 1 here, and then after that, the next electron would go in this 3s right in here, because that's going to be the lower energy level compared to these energy levels in here. Now, if you think about the electrons that are right in here compared to the electrons that are right in here, the electrons that are right in here are going to experience a stronger force, and that's because the electrons are going to be negative, so they'll have a negative charge, and then we have these protons over here that have this positive charge, and so there's going to be an attraction between these, and that's going to be described by a force. And this force will be equal to K, which is a constant, and then we have Q1 times Q2 divided by R squared, which is the distance between the protons and this electron that we're interested in. And this right in here, this Q, that can represent the charge of the protons, and this Q right here can represent the charge of the electron, and this R here would represent the distance between this one here, electron, and then this these protons right in here. And so you can see that as we move into this higher energy level, the force would actually become weaker. And so if we go from talking about this force in blue to maybe this force right in here that's going to be in green, we can see that there's the protons, the number of protons will stay the same. And if I'm comparing this electron in here with this electron in here, the charges, so the Q's, would be the same, but what changed is the distance, right? The green has a larger distance to travel than this 1s right in here, this blue, and so this these electrons in here would experience a weaker force. And so you can keep that in mind when we talk about taking electrons and removing them. So if we were to remove this electron, it would be a lot easier than removing something like an electron in here, because the electrons in here have a smaller force. And so let's now look at the electron configuration for something like oxygen. Whenever we go and remove an electron and put it to a higher energy level, and that would look something kind of like this. And so we can see here that we have 1s2, 2s1, and then 2p5. So what happened from here to here is that we took an electron in the 2s and we moved it over here to this 2p in here. So these have the same number of electrons, but the difference is that we have an extra electron in this 2p over here, and we have one less in this 2s right in here. And so what happened was we took an electron right in here, and then we moved it from here to over here in this area. And so we can put that electron in there, and this would represent the excited state. This is going to be excited, and this over here how the electrons would occupy the energy levels in their lowest energy state, that's going to be called the ground state. So we have a ground state, and then we have an excited state. And in order to take an electron from this 2s to move to this 2p over here, we have to put in some energy. And that energy is going to be equal to h, which is Planck's constant, times f, which is going to be the frequency. And h, they're going to give you h on the equation sheet, and h is going to be equal to 6.62 times 10 to the negative 34, and that's going to be meters squared times a kilogram per second. And what this equation right here means is that as we go from a ground state to an excited state, we're going to be absorbing some energy. And this right here describes the energy that's going to be absorbed. And if you go from an excited state to this ground state over here, energy is going to be released. And that same amount of energy that's going to be that was absorbed will be the same amount that's going to be released. And this equation right here describes the energy both absorbed and released. And so you could think about this as like a if you had like one of those old shirts that you leave out in the sun or the light, and it absorbs a lot of energy, and then if you turn the lights out, the shirt will then glow. That's kind of like what the what's going on here. We're going to absorb some amount of energy from the light, and then after that, the shirt will release that light, and that light will then glow, and that energy is going to be equal to h times f. So when energy right here is going to be released, that's going to be released in the form of light. And so we'll put light here, and we need to go over just a very basic overview of what light is. And so what light is, it's an electromagnetic wave. So I can put a wave right here, and this wave is going to be moving in this direction. And if I go from right here of the light, and then I go right here to the light, that's going to be one wavelength. And I'll put a wavelength like that. And if I go from right here to right in here, that's going to be half of a wavelength. And so what a wavelength is as this wave right here is moving towards the right over here, you can imagine a wall being right in here. And so as this light is moving like basically into the wall, the wavelength will be one full cycle of the wave. And so if you think, if we start right here and we're going to be traveling down this wave, and you want to go to the next point on this wave, we're also traveling down. And so if you move along this wave and you come right in here, you'll reach this point right here. And so notice that we're on the same point, and we're also going to be moving down like this. And so that's how you know this is going to be one wavelength. If you get 2 points kind of like maybe like right here and right here, this is not a wavelength, these 2 points right here, because this part of the wave, I'm moving down, and yeah, I'm on the same point right here, but if you look at it, I'm moving up. And so this right here would be half of a wavelength. You would need to go from here to right here, because at this point in the wave, we're moving down, and then when you get over to this point of the wave, notice that you're on the same point, and you're also going to be moving down like this. So this would, from this point to this point, will be one wave. And that's how you're going to calculate a wavelength. And the frequency, which is described in this equation right here, the frequency is going to be the number of times one wave completes a whole cycle per second. So if we have the speed of the wave, and for light, the speed of a wave is going to be 3 times 10 to the 8 meters per second. And the speed is always going to be the wavelength times the frequency. So if the speed of the wave is equal to the wavelength times the frequency, and let's say we're given the speed and we're given the wavelength, well, if we just rearrange this equation by dividing by the wavelength on both sides, we're going to get the speed of the wave divided by the wavelength is equal to the frequency. And now what we can do is we can say, okay, this right here is frequency. We can substitute that into here, and we'll also get an equation that looks kind of like this. We'll get that the energy is going to be equal to h, which is Planck's constant, times c divided by the wavelength. And c is kind of like h, it's a constant, it's going to equal 3 times 10 to the 8 meters per second. And so let's try to do example question number 3. In example question 3, it says, which of the following atoms has 2 electrons in the highest occupied energy sublevel? And so one way to do this question is to write the electron configurations of each of these. And so if we do that, we end up getting this. And then what we can do is we can go to that that graph that shows the energy levels. And what we can do is we can pull this up. And so the energy sublevel would represent the S, P, D, and F, L values. And so what we can do here is say the S and then the P is right here, and we have the S and the P right here. So the highest sublevel is going to be the P, because the P is a little bit above this S right here. And so if we look at these P right in here, we'll see that we only have 1 electron in here. And so we're looking for 2, so this one would not be it. And then what we could do is we can go to this SN right here, and we can see we have the 5S2, and then we have the 5P2, and so we have 5S here, and then we have the 5P here, and just like before, the P is going to have a higher energy sublevel, and there's going to be 2 electrons in here, so this one does have the 2 electrons that we're looking for. But let's move on to C, and C says we got nitrogen, we got 2S2 and then 2P3. And so we have a 2S2, and then we have a 2P3, and you can see again that the P is going to have a higher energy level, and we're going to have 3 electrons, not the 2 that we're looking for, and so it would not be this one. And then what we can do is go to this oxygen over here, and so we got 2S2, 2P4, so we have the S here, and then we have the P here, and the P again is going to have a higher energy level, and so we have 4 electrons, and we're looking for 2. And so this will not be it. So the answer will be right in here. And another way you can do this problem is to look at the periodic table. And so let's pull a periodic table up. And if we look at this periodic table, we can see that we got the SN right here. And we know that this part of the periodic table is going to be the P block. And so the P is going to be higher over here than this S right there. And so we're looking for 2 electrons in the P. So we have 1 electron here and then 2 electrons in there. And so that would match up this SN right in here. So everything in this column right here would have 2 electrons in the P sublevel. So now let's look at how we can write electron configurations for charged atoms. So to understand how we can write the electron configuration for different charged atoms, let's take a look at the electron configuration for something like iron. And here's the electron configuration for iron, and each of these electrons are in their ground state whenever iron is going to be neutral. And what we want to do is we want to remove 3 electrons so we can get the electron configuration for Fe with the +3 charge. And so in order to do that, when I remove electrons from an atom, I'm always going to remove electrons from the outer shell first. And so this right here, this 4s, that's going to be the outer electrons. And I know that because this N value is a 4, and that's the highest N value of all these electrons in this electron configuration right here. And so what I'm going to do is, if I remove these 2 electrons in here, that's going to be Fe with a +2 charge. But if I want to get a +3 charge, I have to remove 1 more. And so I can either pull from here, here, or here, because the N equals 3 is the next outermost electrons that's in this atom. And so what I'm going to do is I'm always going to pull from the D, and then I'll pull from the P, and then I'll pull from the S. And so if I want to remove 1 more electron, I'm going to remove an electron from the 3D orbital. And so this goes from maybe in 3D6 to 3D5, and this will be the electron configuration for Fe with the +3 charge. And so that's going to look like this. So now let's look at the electron configuration if we want to add electrons. And so what we'll do is we'll pull up the electron configuration for something like nitrogen, which is going to look like this. And let's say that instead of taking away electrons to get a positive charge, let's say I'm going to add electrons. And whenever I add electrons, I'm going to have to add electrons to this 2p, because that's kind of where I left off whenever I did the electron configuration for nitrogen. And so what I'm going to do is I'm going to add 3 more electrons to this 2p right here, and that's going to get me 2p6. And so this is the electron configuration for nitrogen with the -3 charge, and this is nitrogen with the neutral charge. And you might be thinking, well, this right here, this electron configuration, that's the same electron configuration for neon. So both nitrogen with the -3 charge and neon, because they have the same number of electrons and the same set of quantum numbers, they're going to be called isoelectric. And so neon, Ne, and nitrogen with a 3 minus charge, these are going to be isoelectric, which just means they have the same number of electrons and the same electron configuration. So let's now try example question 4. And example question 4 says, which of the following accurately describes the electron configuration of Fe and Ni2+. So to figure this out, we have to know the electron configuration of Fe and of Ni. And so let's first pull up the electron configuration of Ni when it's not charged. And that's going to look like this. And what this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. Now, if this is the electron configuration when Ni is going to be neutral, and we want to have it a 2+ charge, what we need to do is we need to get rid of 2 electrons in this electron configuration, and we need to pull electrons from the highest N value, and that's going to be this 4s right here. So if we pull these 2 electrons out, this will be the new electron configuration for Ni2+. It's going to have the 3p6 and 3d8. And so what we want to do is we want to compare this electron configuration with the electron configuration of Fe. And the electron configuration of Fe is going to look like this. So what we can do here is compare these 2 electron configurations and then look at the answer choices and see which one matches up. And if you look at C right here, it says that Fe can be written using the shorthand notation and Ni2+ cannot. Well, that's not true. We can use the shorthand notation for both of these. And so C would be out. And so now what we're going to do is we're going to look at these answer choices, and we can see here that if we have Fe has 2 electrons in the 4s orbital, let's see if that's right. So here's Fe, and it does have 2 electrons in this 4s orbital. This superscript 2 right in here, that's going to represent the 2 electrons. And if we look at the Ni2+, we can look and see that in the 4s, it doesn't have any because we had to remove those to make this an Ni2+. And so this one would be the correct answer. The answer choice would be A. So now let's move on to section 1.6 and talk about photoelectron spectroscopy. So in section 1.6, we're going to talk about photoelectron spectroscopy. And what that is, it's a technique that measures the relative energies of electrons and atoms and molecules. But for the AP exam, we're going to focus on the atoms. And you could think of it as the amount of energy that's going to be required to remove an electron. And we can pull up a photoelectron spectroscopy graph of something like carbon, and that's going to look kind of like this. And so here's carbon right here, and these different peaks right here, those represent the binding energy that's going to be required to remove a particular set of electrons that's going to be within this carbon right here. And this right here is the amount of binding energy, and over here we have the number of electrons. And what we can do is we can write the electron configuration for carbon, and that's going to be 1s2, 2s2, and then 2p2 like this. And so this right here, the peak right here, that's going to represent the 1s2 orbital. And the reason why these electrons in here have a higher binding energy than the electrons over here is because these electrons over here are going to be closer to the center of carbon, and in the center, that's where the protons are. And so we can pull up a picture of that like this. And you can see the protons are going to be right here, and you have electrons in this orbital right in here, and they're going to have a stronger force. We'll call this like force 1 right here, and they're going to have a stronger force than the electrons that are going to be over here, and we can call this right here force 2. And so we can see here that force 1 will be stronger than force 2. And the equation for this force is going to be Coulomb's law. And Coulomb's law says that the force is going to be equal to some K constant right here times Q1, where Q1 can represent the protons or the electron. And then we have Q2. And Q2 would represent the opposite of whatever Q1 is. So if Q1 is going to be the protons, Q2 would be the electrons. And we're going to divide that by r squared. And r is going to represent the distance from the center to the electrons that we're going to be referring to for that particular force. And so you can see here that the distance from here to here is going to be smaller than the distance from here to here. And so basically, if we're able to decrease the r value by decreasing the distance, then that's going to increase the force over here. And these q values are going to be the same for this one and for this one. And so let's say like these electrons can represent q1. Well, then the protons would be the q2. So because F2 is going to be smaller than force 1 over here, it means that the electrons that are going to be right in here are going to have a higher binding energy than the electrons that are going to be over here. And basically, the stronger the force that's holding an electron to an atom, the harder it is it's going to be to remove that electron. And that binding energy, the equation for it is going to be U, and that's going to be equal to K, which is going to be the same constant as the Coulomb's equation, times Q1 times Q2, and we're going to divide it by R. And R is still going to be the distance from one charge to the next, and Q1 and Q2 are going to represent the protons and then the electrons, the charge of each of those. And what you need to know is that the greater the force, the greater the energy is going to be required to remove an electron. And if we were to put in energy in this atom, and we were to try to remove an electron, as we increase more and more energy, we would first get to this one right in here, this amount of energy right here, and that's going to be the least amount of energy. That's because these electrons that are going to be right in here are going to be farthest away from the center, and this energy was also going to be equal to H, which is Planck's constant, times F. And whenever I use this equation, you want to make sure your units right here are all matched up. And so the units for this equation is going to be the energy we measured in joules, and H is Planck's constant, and then the frequency is going to be 1 over a second. And so let's use this information to do example question number 5. So example question 5 says, based on the photoelectron spectrum, what is the minimum frequency of electromagnetic radiation required to ionize an atom to form X with a positive charge? And here is the photoelectron spectrum, and see if you can figure this problem out. So example question 5 says, based on the photoelectron spectrum, what is the minimum frequency of electromagnetic radiation required to ionize an atom to form X with a positive charge? And so this is the photoelectron spectrum for this X chemical, and we want to make this a positive charge. And so we're going to have to remove an electron. And so we're going to remove this set of electrons right here, or this just one electron. And whenever we do that, we're going to get this this chemical with a positive charge. And so what we're going to do is we're going to have to take this number here and convert it to joules. And right now we're in megajoules per mole. So what I'm going to do is I'm going to take 0.58, and this will be megajoules per mole. And I need to convert this to joules, because the equation is going to be equal to this. The energy is equal to H times F, where H is going to be Planck's constant. And so what I'm doing here is I'm taking this energy and making it just in joules, so I can use this right here. And so we have 0.58 megajoules per mole. We're going to multiply that by, we'll put 1 mole up here, and then we'll multiply by 1 and divide by Avogadro's number, which is 6.022 times 10 to the 23rd power. And that will get rid of this moles here, and moles here can cancel out. And then we want to go from this megajoules to just joules. And so what we'll do is we'll put a megajoule on the bottom, and then we'll put joules up top. And then for every one of these megajoules, we're going to get 1 and then 6 zeros, 1, 2, 3, 4, 5, 6 joules. And so what will happen is these megajoules there cancel out, and we'll be left with joules. And when we do this calculation, this conversion factor, we're going to get, this is going to be equal to 9.63 times 10 to the negative 19 joules. And so what I'll do is I'll take this number and plug it into my energy equation in here. And so that's going to be 9.63 times 10 to the negative 19. And that's going to be equal to Planck's constant, which is right here. That's going to be 6.6 times 10 to the negative 34. And then we're going to multiply by the frequency. So frequency is right here. And we're going to solve this now for frequency. And so when we divide both of these sides of the equation by Planck's constant, we're going to get this right here. And then this will cancel out. And then we'll divide by the same thing on this side. We'll do 6.6 times 10 to negative 34. And we'll get that the frequency is going to be equal to 1.45 times 10 to the 15th power. And the units for this are going to be a second raised to the negative 1, or a per second. So here is going to be the frequency of the amount of energy that we would have to put in to remove one of these electrons right here, and to remove that. And then we would get this atom with the positive charge. And so now let's look at how the number of protons can influence this binding energy. So now let's take a look at the electron configuration for hydrogen and helium. And so if we take hydrogen, the electron configuration for it is going to be 1s1. And then for helium, it's going to be 1s2. And what we can do is we'll make a diagram for each of these for what those electrons look like. And so for hydrogen, we have 1 proton. So I'll put 1 proton in here. And then we're going to do 1 electron, and it's going to go around kind of like this. And then for helium, we're going to have 2 protons. And we're going to focus just on 1 electron for helium. And so we'll put that 1 electron right here. And it's going to go around kind of similar to this hydrogen right here, because they both are going to be the n equals 1 value away from the center. So this is n equals 1 here. And this right here is also going to be n equal to 1. And so if we want to remove an electron from here, what we want to do is we want to overcome the force that's keeping this electron towards the center like this. And so that force is going to be equal to K, which is a constant, times Q1 times Q2 divided by R squared. And so because this 1 proton right here can be this Q1, and then this 1 electron here can be Q2, this force over here is going to be smaller, this F1, than over here for this like F2. And that's because this 2 protons in here, that can represent this Q1. And this 1 electron can represent this Q2 right here. And so what we can do is say that F2 will be greater than F1. And so more energy is required to remove an electron from here because of their because I have more protons in here. And when you have more protons, that's going to be called its nuclear charge. And so we'll put that the number of protons that an atom has, number of protons, that is basically going to be equal to the nuclear charge. And so anytime you see the words nuclear charge, they're talking about the number of protons in here. And so let's pull up a photoelectron spectrum of both hydrogen and helium so we can compare the two. And that's going to look kind of like this. And so you can see here that we have hydrogen right here and helium over here. And you'll notice that this energy right here is going to be smaller than this energy over here. Even though they're the same distance away from the center, the reason why the hydrogen has a smaller binding energy is because it's going to require less force to remove this electron because it's got a smaller nuclear charge. And so if you're given two graphs like this, where you didn't know this was hydrogen and this was helium, you need to be able to determine that this one's going to be hydrogen because it has the smaller nuclear charge than of this one over here. And so now let's look at how electrons within the same orbital, or the m sub L, can influence the bonding energy. And so we have nitrogen, oxygen, and fluorine. And what we'll do is we'll put down the electron configuration orbitals, kind of like this. So these are the electrons right here that we're going to be concerned about, because those are going to be the outer electrons. And so what we'll do is just put we'll put 2s right here, and these are 2 electrons there, so we're going to do up arrow and then down arrow. And then we have this 2p right here, and p is going to have an m sub L of -1, 0, and +1. And so we're going to give it 3 lines like this for the -1, 0, and +1. And so this will be the 2px, the 2py, and then the 2pz right here. And so we have these 3 electrons in here. So we're going to do one up, arrow up, one up, and then one up to space all the electrons out as much as we can. And so we're going to go ahead and do the same thing for the oxygen and the fluorine. And so that's going to look pretty similar. So we're going to do 2s and then have 2 arrows, one up and one down there. And then we have the 2px, the 2py, and then the 2pz. And what we'll do is just put an up arrow because we have 4, so that's 1, 2, 3, and now we have to double up. So we're going to double up one of these right here to fit 4 electrons in here. And then for the F, we're going to have 2s, and then we'll have an up arrow and a down arrow. And then we'll have the P in here. So this is going to be the 2px, 2py, and then this will be the 2p Z right here. And we got to fit these 5 electrons, so that's going to be 1, 2, 3, and then we have to double up, so this will be 4 and then 5 in here. And what we're going to do is we're going to remove 1 electron from these for the ionization energy. And so what that's going to look like is this: one of these electrons is going to be removed. And if we do it for this one now, these 2 electrons in here are going to repel each other. And so because electrons are going to repel, it's actually going to be easier to remove one of these electrons out of here. And then the same thing is going to happen over here. It's going to be easier to remove one of these. And so even though that the number of protons increases, the binding energy would actually decrease as we go from N to O, and then increase as we go from O to F. And so if we were to pull up a photoelectron spectroscopy graph, it will look kind of like this. And so here are the photoelectron spectroscopy graphs for nitrogen, oxygen, and fluorine. And what you'll notice about this is that the nitrogen has a binding energy of 1.4, and the binding energy for oxygen is 1.31, and the binding energy for fluorine is 1.68. And so these are all the minimum amount of energy required to remove 1 electron. And the reason why this one is lower is because of this 2 electrons in here that are going to be repelling each other. And so as you go right and up the periodic table, the binding energy typically increases, but there is a small kink in the chain as you go from nitrogen to oxygen to fluorine, and that's because of this lone pair right in here. And that's true for each case where you have electrons in the outer orbital in this p, and then as you fill up the p where you have at least 2 electrons in here, the binding energy will go down some, and then it goes back up. And so now let's take a look at the 2 types of photoelectron spectroscopy graphs that you're going to see on the AP Chemistry exam. And so one type of photoelectron spectroscopy graph that you might see might look something like this. And this is the photoelectron spectroscopy graph for sodium, and this is going to be called the full photoelectron spectroscopy graph, and that's because it gives each electron's binding energy. And this peak right here would represent the 1s, this peak right in here would represent the 2s, this one right here would be the 2p, and this one over here would represent the 3s. And so you have the binding energies of each of them, that's in this sodium right in here. And so another way they might give this to you could look something like this. And in this graph, we only have this peak right in here. And so this is going to be called the partial photoelectron spectroscopy graph. And this right here, this peak in here, would be the 2s. And so one reason they might give you this graph instead of this graph is because they might give you two different atoms where you have this peak right in here, and they might give you another peak that might also be the 2s. And what they want you to probably do is to compare how much energy it would take to remove an electron from a particular orbital, in this case the 2s. And the reason why that would be important is because if you think back to the equation that the force to remove an electron would be equal to K, it's a constant, times Q1, Q2 divided by R squared. And so you want to think about the force required to remove an electron. And if you're comparing this 2s with a different atom that's got an also 2s, well, the R value is going to be the same because this value here, that 2, that's the n value, and that represents the distance away from the center. And so that's one reason why they might give you this graph instead of this graph over here. So you might either see a full or a partial. And another type of graph that they might give you might look something like this. And in this graph of sodium, we don't have the numbers on this y-axis over here. And so what we do have are these different peaks. And you need to know that as you go from one peak to the next, you must have change orbitals. And so if this peak is going to represent the 1s, and then the next orbital will represent the 2s, it means that before you fill up this orbital to go to this one, you have to put in 2 electrons. So this peak right here goes up to this first line. So that must mean that this first line right here is going to represent 2 electrons. And so we're going to have 2 electrons for each line. So if this line represents 2 electrons, that means that this line right here will have to represent 4 electrons. And then this line up here at the very top will have to represent 6 electrons. And so they might give it to you with these numbers on this y-axis here, or they might leave them off and you would have to figure out what they are. And so let's use information to do example question number 6. And example question 6 says the 2 photoelectron spectra graphs shows the energy required to remove a 1s electron. One of the graphs is for nitrogen and the other is for beryllium. Which of the following graphs represents the nitrogen atom and why? So to solve this problem, we need to go to the periodic table and look at the electron configuration for nitrogen and for beryllium. So if we go to the periodic table, we're going to see that we have beryllium right here, and then we have nitrogen right here. And beryllium is going to have 4 electrons, and nitrogen is going to have 7 electrons. And what that means is for nitrogen, it's going to have 7 protons in the middle. And if we're talking about the 1s electron in both of these cases, then the n value is going to be the same for both. So this is going to be n equal to 1. And here's going to be the electron. And so it's going to go around the nucleus kind of like this. And we also have this beryllium over here. And so beryllium is going to have 4 protons in the middle. So we'll put 4 protons. And we're still talking about the same 1s electron. And so we're still going to be this n equal to 1 over here. And so here's the electron, and it's going to go around like this. And if we want to compare the binding energies of both of these, the equation that we're going to use is going to be that the binding energy, or U, is going to be equal to K, Q1, Q2 divided by R. And because this n value and this n value are exactly the same, it means that this R right here will be exactly the same. And because we're moving 1 electron here and 1 electron here, each of these electrons have the same charge. And so this Q right here, it's going to be the same for both of them. This Q1 can represent the charge of 1 electron. And so the difference would be this Q2 right in here. And for this, it's going to be 7 protons will be the Q2 for the nitrogen. And then over here, the 4 protons will be the Q2 in this equation right here. And so because this number is larger, it means that this binding energy right here is going to be larger. And so this one would have a a stronger binding energy. And so if we look at both of these graphs, you'll see that this one right here has a higher binding energy. And so graph 1 would represent nitrogen, and then graph 2 would represent beryllium. So the correct answer choice is going to be A.